Hello, everyone. Welcome to yet another new seminar in Connect Them All seminar series. My name is Saurabh Band, and I'm your host for today. So, let me start by introducing myself. I am a research assistant at the University of Bremen in Germany. I'm also pursuing my PhD at Department of Commerce in University of Bremen. And today we have a special guest. Please welcome Dr. Marco Zúñiga. Hello, Marco. Welcome to the seminar series. And please allow me to introduce you to our audience. Dr. Marco Zúñiga is an associate professor in Network System Group at TU Delft. He obtained his PhD and master's degree in electrical engineering from University of Southern California, Los Angeles. His research interests are in area of IoT, mobile computing, and visible light communication. Dr. Zúñiga has also received an Essential Innovation Award in 2017. And today he will talk about his work titled Sunlight for Wireless Communication. So Marco, the floor is all yours.
Thank you, Sora, for the introduction. And now we are going to start with this talk. I guess everybody can hear me well and you can see the slides, right? Yeah. Okay, so I usually use this cozy room to try to describe what this talk is going to be about. So imagine that you are in that living room, sitting in that chair, and you have, let's say, your laptop on top of you, and you're just getting data. How do we get data most of these days? Is mainly via wireless technologies, right? So you have, for instance, your Wi-Fi station, and then that's the device that is going to giving you all the data that you want. But now, over the last years, there has been a new technology called visible light communication. And they use the lights that you have on top of you, like that light that you see there. It could start modulating information, and then that light can start giving you the same data that you receive through your Wi-Fi device, right? So we go from radio waves to visible light waves. But now what we are doing in my team also is to see, maybe what we can do is use sunlight to provide also some of that communication. And that's going to be the topic that we are going to be covering. This talk has three main parts. The first one is going to be about, let me put one here. The first part is to describe why we need to overcome some of the limitations of radio frequency communication. The second part is going to talk about how we change the spectrum from radio to light and how we communicate that data. And the third part is going to be about the title of this talk, about using sunlight for wireless communication. Okay, so that's roughly the main idea. And if you have any questions, please just write it there in the comments, and then I will try to answer them immediately. So before proceeding, I want to give credit to the teams of PhD students in my group. Here you can see all of them. A lot of this work, of course, would not be possible without their great effort. So thanks to them. Now, let's start with the first part of this talk, which is radio frequency is really good, but what are the limitations that they have for us to move into light? So the way that I usually start this to put things in context is to have you listen to one sound. Let me just change from pen now to the pointer. So listen to that sound. So for many of you, that sound will be very familiar. For some of you, if you're very young, it will not. So that's the sound that we use, right, to connect to the internet. That was in the beginning of the 2000s. And since I put this here. So the first internet message was transmitted in 1969. And for the first 30 years, so roughly up to here, we were using cables to communicate with the internet. Not only that, only 5% of the population, of the world population, were roughly connected, and we have very low data rates, 50 kbps or so. What happened after that? Well, now around 60% of the world population is connected to the internet. They are using mainly wireless technologies, and on top of that, the data rates have increased. Furthermore, we have the Internet of Things that is adding millions and millions of devices that are using mainly wireless communication. So what is the message of all of this is that over the last 2 decades, wireless communication has exploded. It has become a fundamental pillar of modern societies. And this is having a few consequences. The most important one is just basic economics. If too many people or you want too much of something, that is going to become scarce and expensive. So how scarce and expensive now is radio frequency communication? In this slide, you can see the distribution of the radio spectrum. Every country has an image like this. This one is for the United States. And the first impression that it gives you is that it's pretty crowded. All these technologies that we use, right? 4G, 5G, LoRa, Wi-Fi, Bluetooth, all of them, AM, FM radios are somewhere there. Now, what is important to consider is the following. Over the last decades, we have improved the capacity of our networks. That means that we are transmitting more and more and more data. And you may think that a lot of that improvement is because we are coming up with very smart decoding or encoding algorithms, and that's not the case. So around between 2 and 5 times of the improvement has been just because we are having better decoding and encoding methods. But most of the improvements is just because we are using spatial reuse. So we are, instead of having a very broad coverage, we are having a narrower and narrower coverage. So in that way, we can reuse, right? Spatial reuse. But one thing that is also very important has been that we are getting more bandwidth. We are able to use more and more bandwidth. And that's important because if you see Shannon's equation, you see that the capacity of your channel, that is how much data you can transmit over your channel, depends fundamentally on these 2 factors, the amount of bandwidth and the signal-to-noise ratio. But there's a difference. This is growing, this helps linearly, and this only logarithmically. So what we are going to see is that if this acts in this plot, if I give you more bandwidth, if I give you 16 times more bandwidth, you're going to have 16 times more capacity. But if I give you 16 times more signal strength, you're going to have only a 4 times improvement. So it's only logarithmic. So now, because bandwidth gives you this linear improvement, there's a high demand for it. Everybody wants it. Now I will do a quick animation on this slide, and let's see if you see the difference. Okay, there's a minor difference there. That little spot that you observe, for those of you that could not see it, is here, is the C-band. It was recently auctioned in the US, and it was the most expensive band up to date. How expensive? More than 80 billions. So then what I started looking was for the market capitalization of some companies, and that's equivalent to the 200 most valuable company in the world, or you could buy the 3 most profitable airlines and still have money left. And that's just the resource. That's how expensive and valuable bandwidth has become. So now that was the first part, the motivation to see what radio is wonderful, but what are some of the limitations that we are facing? That's one. So researchers started looking around 20 years ago with the invention of the LED into the visible light spectrum. So from a physics perspective, both radio and light are electromagnetic waves. But if we see them, the spectrum that is for radio is just getting super congested. We have 4G, as I said, 5G, LoRa, Wi-Fi, you name it. Almost all the wireless communication that we have had over the last century, including AM, FM radio, right, has been relying on this single pillar. And on the other hand, we have the light spectrum that it has kind of been there, sitting empty, and it's free, and it's not regulated. So how does this work? If you have a light, and imagine that you're with a friend, and you want to communicate with that friend at night, and you have a flashlight. What do? You turn your flashlight on and off, right? So you start switching it on and off to something like Morse code.
Yeah.
If you increase the frequency of the modulation, let's say to a few hundred hertz, the human eye will see a normal light. So your eye will just see the image that you see here, but a photosensor, in this case is a camera, will see patterns. So this is the same idea as what happens with movies, right? So movies are just a series of images, static images, but they happen so fast that it gives us the impression of continuity. In the same way, if you start modulating light intensity, there's going to be a point beyond which you see a normal light on. So you will be under that light. Let's imagine that is the light on top of me. You open a book, you can read your book, but at the same time, if you put your laptop or your phone, you can start getting all that internet data through that at very high speeds. So there are already companies that can sell these products. But it's not only this communication that it can give you, which is called, the technology is called Li-Fi, so for light fidelity.
Mm-hmm.
But you can do many other things with visible light communication. So, for example, here, there's one work by Disney Research in which you have a magic wand. So I'm not sure if you will see it here, but there's this little piece over there. It's just a light. It's oscillating. Your eyes will not see the changes. But if it gets close to the dress of the other girl that is there, it will explode in different color patterns. Because you can have photodiodes, and then you start communicating. So that's the idea. Now, almost every LED that you see in your environment can be transformed into a wireless transmitter. So cars can talk to each other through the LED lights that they are there. You can also use the LEDs in appliances, in your dishwasher or your night lamps. Every single light could be transformed into wireless transmitter. And that's one of the advantages that is coming with visible light communication. Now we'll show you a video of something that we did in my group that will give you also some other advantages. So in this video, what you will see is this light is modulating information. It's happening so fast, of course, that your eye is not seeing. And then on the top, there's a receiver. And we are moving the receiver. And as you can see, we can obtain the location of that receiver. There's some more inertial sensor units on the receiver, but the key idea is this. If you have a GPS, you need roughly at least four or five satellites to give you a location in 3D. And here we are doing that with a single anchor point. And that's an extra benefit of light. It has a particular radiation pattern. And if you do some mathematics on them, you only need that one anchor point to do localization. There are also companies that provide these systems to do localization in indoor environments already. Okay, so this is another advantage.
Yeah, so Marco, sorry to interrupt you, but I have one question here. So you say that you can use a single source of light to track the location. In this case, like, is there a limit on minimum threshold or minimum intensity of light that is required for this to work?
Good question. So then let me go back here and let me try to explain it. So in terms of intensity, yes. So what you could see is that this light follows sort of a Lambertian pattern. So I'm not sure if you can see what I'm drawing here. Actually, let me just use red. Maybe red will be better. So this is this Lambertian pattern. If you go too far away, you will not be able to receive the signal. And that's okay. But roughly what is going internally is that when you have a given position, your receiver is going to see one Lambertian pattern. And when you move into a different location or rotation, you're going to see a different Lambertian pattern. And it's the intersection of these two, the one that is going to give you your localization. So the fundamentals of it, of course, always depend on signal strength. That's what happens with every communication system, wireless communication system. But the key idea about why this requires only one anchor point is because the radiation pattern has something called a Lambertian radiation pattern. And that's the key to achieve the localization with just one anchor point.
Yes, okay, thank you.
Welcome. So, but we can also do a few other things, not only communication, but we can also do sensing. What you will see here is we are using color sensors. So this was work done with a company, Tridonics, now it's called Zumtobel. It's a big lighting company. And what they had is, on top of their lighting, they had color sensors. So the one that you observe here. A color sensor could be seen as a single pixel camera. That means that it will combine all the colors under the field of view and represent it as a single point. So for example, if you have black and white, the color will be gray. So what we wanted to do is to see if we could track people just using a color sensor, not with cameras, because we don't want to invade privacy. The key idea is that as this person starts walking, these color sensors first will have a baseline, which is the combined color of the floor. Then as the shoes start coming, it will be darker. Then we have the color of the skin. It will mix with the color of the dress, the skin again, and the hair. And what it will do is in time, if x-axis is the time, the y-axis will give you some sort of a unique feature that is the contour of that person in terms of the colors that you are being observing, right? So here we have an experiment. There's going to be one color sensor here. It's on top of this wood that you see there with beam, and another color sensor there. And at the beginning, you will see one person passing through both of them. And notice that they have a blue sort of a jacket, black hair, and dark pants. And later, there will be another person passing through both of those color sensors. And it's going to have just, let's say, some differences in the color. So the pants, you will see that they are still dark hair, and this turquoise jacket. So now, how does the system work? First, it's going to be passing through the first sensor, and then you will see that we start detecting the signals. So those dots that you see they're changing are capturing that unique feature of the first person that is passing by. Then we put that into a database and we said, do we have a similar signature somewhere there? And we apply some machine learning techniques and signal processing techniques to do that. If there's no such a signature, then by the time that you pass through the second sensor, you will be able to see that the same person has passed through both of them. When the second person starts passing by, we will see a different signature that is going to be appearing. So a series of dots, those ones that you observe there. We will see if that's already in the database. It's not, and then we will see, well, this belongs to a different person, right? So clearly, this could be easily tricked if you just take off your jacket or your sweater.
Yes.
But the basic idea is that you can just start exploiting this ambient light that is out there to achieve not only communication, but some level of sensing. By the way, so for many of the things that I'm talking, what is related to the work in my group, the title of the paper and the venue is going to be at the bottom of the slides. Okay, so now we have gone from radio to light, and we have stated that the benefit is that we have an empty spectrum. But there's a problem with these two technologies, and that's the energy consumption. Why? Because if you think about it, wireless communication boils down to just moving energy from one point to the other, right? So you need, let's say that you have an antenna, a radio antenna or a light, then you need energy first, and then after that, it will start going down, and hopefully will be above the sensitivity threshold of your receiver. But in that process, we are moving energy from point A to point B. And during that travel, we are dissipating a lot of it. So this moving energy from one side to the other is what makes wireless communication or communication in general very expensive. Now, how expensive? There was this article in Times Magazine. It was in 2013, so 10 years ago. And it was surprising because it mentioned that the amount of energy that we humans use for digital communication is 50% more than the amount of energy that we use to move all airplanes around the world. So that's the power of just, sending all of these videos and all of these things around. If we want to have a sustainable means of communication, we clearly need to do something with that. Now, this amount of energy was for both wired and wireless, but wireless, of course, consumes a big chunk of that. So now, let me just give you a quick comparison between this active visible light communication and the next topic, which is going to be the communication with ambient light. So let's just recap briefly. What we have mentioned is that if you go from RF to visible light, the main improvement that you have is on the spectrum. You get some more spectrum, but both of them consume quite a lot of power. Now, actually, visible light communication, it depends. What do I mean by that? If you have a Wi-Fi station, it consumes a few watts. A light bulb consumes several more watts. But if you use light for communication, let's say at night, when you already need illumination, it's a good thing. Why? Because illumination in that case will consume roughly, let's say, 80% of the energy. So you need to turn on that light to see. If on top of that, you want communication, you at a 20% extra cost. And that's okay. But if what you have is already natural light, let's say sunlight, and you want to turn on your LED only for the purposes of communication, then it's not a good idea because this illumination is already an energy cost that you do not need, right? So this visible light communication technology with LEDs is good for bandwidth, but it still has similar drawbacks to radio in terms of energy. So now we would like to see if we can exploit sunlight. And that's where we are entering the main topic of this presentation. So what is the idea? The idea is just, let's say that you have this beautiful sunlight that is coming from somewhere. Let me change this to red. So you have your sun. Energy is coming all the way from there, all right? And instead of turning an LED to get that communication or radio, let's take advantage of the energy that is already in sunlight as a wireless carrier, so then we can start modulating it and transmit information. Right? So that's the key idea, to take advantage of that pervasive and vast amount of energy that is out there. What is the problem? With an LED, we can turn it on and off. An LED is a light-emitting diode. It's just like a diode, so it's an electronic component that we can switch on and off as we wish and at very high speeds. It would be wonderful if we could switch the sun on and off, and then that will provide a broadcast channel to the Earth for free, taking advantage of that vast power. Clearly, we cannot do that. But there are ways to modulate sunlight in an indirect manner. For example, mirrors, heliographs, right? And before radio existed, this was the way in which we achieve relatively long-distance communication in a wireless manner. These mirrors, at least, were used by European armies until the beginning of the 1900s to achieve several kilometers of distance in terms of range. Then radio came. We invested a lot of it. It has a lot of benefits, of course. And then kind of light was a little bit forgotten. But this is the idea now that we have improvements in optical technologies. Can we take this whole idea and revisit and see what it could be done? So that's what we are doing in the group. So I also do research on active visible light communication that is with LEDs, but in this talk I'm focusing on the work that we are doing with passive, that is with just natural light. Here first, let me give you an example of one of the experiments that we are doing, or that we did. This was in collaboration with INVEA Networks. And if you remember, we were sensing people before just by the contour that they have, and here we are going to do the same thing for cities. This is roughly the same idea as having a barcode reader, but instead of having it for superstores or supermarkets, to have it for cities. So you could see the concept as follows. So in a supermarket, we have this sort of barcode reader, right, that is emitting some light, laser, infrared. But instead of having that light, let's say, why don't we use sunlight? Then you have a photodiode or a photosensor inside that is just reading what is backscattered. Instead of having one, why don't we deploy multiple sensors? Photodiodes are inexpensive, and they can work just with a small solar cell. And instead of having just the items with barcode readers, why don't we start analyzing the reflections that can happen in our cities? So that was the idea. What can we learn just by these simple reflections? And in these images that you see on the right, we see two cars. Both cars are white, relatively similar models. And then in a parking lot, they were driving around, and we had just this simple photodiode on the top. So as they were moving around, we can see that we are capturing their reflection. So this x-axis is time, the y-axis is the received signal strength. And something that you notice is that in spite of both of them being, let's say, almost sedan, hatchback type of vehicles and being white, the signals that are reflected are very different. So we could easily identify just the type of car by applying machine learning methods, signal processing methods on top of these signals. Once again, the importance of this thing is that we do not use cameras. Huh? We want to be privacy preserved.
Okay, but like here you mentioned that even with the same color, the output is different. Is it because of the material that is used, or why is there exactly difference even if the color is same? Like,
it could range from many different reasons. One of them could be also how clean the car is, maybe for the experiment.
Yes,
so,
yeah, I was going to ask that, yeah.
Yes, and then of course that will change the layout. But
Mm-hmm.
it also depends on just how reflective this paint could be. So the paint exactly for all of them, even though it's white, it reflects the entire wide spectrum, so the entire spectrum of light.
Mm-hmm.
But that doesn't mean necessarily that it's at the same intensity. Now,
Yeah.
but perhaps the most important thing is that you see that the external layout of the car is what causes
Yes.
main differences, right? So it's not only the
Yes.
intensity, but if you see the individual components, that's what is causing the main difference.
Mm. Okay.
Um, and then what you could do is you could add something like a barcode to that, and then you could see your cars as moving mobile packets in which you start receiving, let's say this is the part A, like a preamble, and then you can start embedding some level of information. We just created these horrible barcodes to be placed on top of it, but it doesn't need to be that way. It could be any other optical material that just changes the way in which light is reflected
Mm-hmm.
back.
Yep.
So that was about sensing, but the information that we had there is static. Either the vehicle moves and it only has one type of reflection, or if we put something like a barcode, it's fixed. In order to have communication, of course, we need to have a dynamic way to do that. And how can we do it is by using optical materials that can change the level of transparency of light. Later, we will see another optical material that is like a mirror, but in this case, let's just focus on this. These are roughly based on liquid crystal technologies. It's the same technology that you have on your screen, liquid crystal displays. And the key point is that by varying a few parameters, which could be voltage, you can have different levels of transparencies, as you can observe here. And then that means that light could come, sunlight will come on one way, then we modulate it, and then we can have ones and zeros coming out on the other side.
Mm-hmm.
Actually, these type of materials are not only constrained to just kind of control the light, the illumination coming into the room, but as you see here, there's a studio here in the Netherlands called Studio Roos Harden that combines arts with engineering, and they develop something called DRESS 2.0, and it changes the level of transparency depending on how you feel, right? So it could be a little bit of a dangerous material to play with, but it's just interesting how these new optical alternatives are coming. Now, to give you a more dynamic view of what is going on, you could see this video. Oops. So what you will see is that in order of privacy, you cannot see the office that is behind that panel that is kind of white. But in a moment, you will see that it starts changing the pattern of the light, right? So then now you can see that light goes through. And now you will see that it can be controlled in a finer manner. And that's the basic idea that we can use to start controlling light. Now, in terms of communication, there's a difference between single input and single output systems and multiple input and multiple output systems. So you can see one of those panels. So going back here, one of these panels would be a single pixel, or one of these big areas would be a single pixel. So if you have that area, that's the transmitting pixel, then you have a receiver, which could be a photodiode. Or if you want to increase the data rate of your system, you can have multiple 6 pixels, multiple panels. So that would mean, in this case, for instance, modulating each one of these panels with a different stream of data. And then you have the receivers on the other end decoding the information. And we have done work in both type of cases. And first, I will go with a single input and single output system. The basic idea is it's very simple. It's just basic physics. So I would just put here. You do not need to change that setup. So it's just like in the same way that polarization works, right? So then here you could see that it gets blocked or transparent. That can be done just with electrical pulses. And now we can go back to the slides, please. And you see that liquid crystal displays, which is something small. It's just roughly this big. And it starts changing the level of transparency as we mentioned below. And if we have sunlight or any type of light for that matter on one side, and then on the controller, we just put a small voltage, then we can let the light pass through or block it. And in that way, we can transmit information. Okay, so it's a very basic principle. There are, of course, a lot of challenges to realizing this well, but that's the basic idea. And how could this be used or applied? So imagine, for example, that you are in a city, could be Bremen, could be here in Delft, and you would like to have information about the city, restaurants, museums, things to do, but you do not want to use your data plan. So you just turn on airplane mode, no radio frequencies. Then you can go like this to people that are here with your device, your phone. It has a camera and a photo sensor. And then light is coming from the top, modulated by a smart panel, and it can give you the information that you want, right? So once again, this could be systems that could be deployed and try to exploit in general these transparent surfaces that we have in our cities for communication. Now I will show you one prototype that we have. There's the transmitter. That's the box that you see there. It looks very big there, kind of the size of a tree. It's not. It's just very small. So probably the size of the LC is like the one that I'm showing here with my hands. That's actually here. Let me also use the pen again. So these are the LCs, right? And then we also have a connection for a keyboard, and we have sensors internally. So that's how we create data. Then light will be coming. It will be coming into this direction. It will be modulated with frequency signal shift keying. So the same thing that you have in your radio. Now, the challenge here was to make sure that there's no flickering effects. One important thing that we need to consider with light communication is that compared to radio waves that we cannot see, so we have more flexibility on the modulation. We can see light. So it cannot be too intense, and it cannot cause flickering effects. So it's very important to make sure that that's the case. So that was one of the challenges that we have to face here. So we transmit the data, and at the receiver, we had this box. Also, the box may look big, but it's not that big. It's just something roughly this size. So we have a solar panel, and we have an e-ink display to show the data. Here it says one of our first experiments. I don't know if this is perfect, but it's getting there. So we just show the transmission that is happening just with light. And once again, you could deploy this anywhere where there's sunlight, and you can use it for power and communication. You can also use a solar panel to power a Bluetooth or any type of radio device, of course. But once again, the advantage that we have here is that we are just using light directly, a different type of the spectrum. How does this system perform or work? In this plot that is on the left, the x-axis is frequency, so how fast we start modulating, and there's something called modulation percentage or depth, and the IEEE standards require you to be below these points. So this would be really good, but this is the minimum that you should satisfy. And we can see we tested our systems with different voltage levels. That's how you modulate these LCs. By the way, they consume very little power, a few microwatts each. Most of the cost goes into the processing itself, which is a few tens of milliwatts. So the flicker effect is satisfied according to IEEE standards. And this, we tested it indoors and outdoors. Indoors is using artificial ambient light, so the light that I have, for instance, in my office, and we get a few meters range. But when we go outside, of course, sunlight intensity is much stronger than what we have with indoor lighting, and we can get 50, 60 meter range communication. Now, and here's the first catch. Look at the data rates. They're very low. So 80 bits per second is what we got for the long range, and 1,000 bits per second is for the short range. And in general, if you see single pixel transmitters in the state of the art, most of them are hitting a barrier, probably at 1 kbps for a distance of a few meters. In the next work, what we wanted to do is to improve this point. We said, we would like to have the long range, but we would like to increase the data rate. Okay? And that's what I'm going to explain next. So in this work, this is just our LC. Here is in a transparent state, so light is passing through. Here is in an opaque state, so we are blocking light. And when we modulate the signal, this is the voltage pulse. It takes some time until this signal is actually mapped into a change in the level of transparency. So for example, in this case, this state will be A prime, so transparent. That would be this one that is here. And this end of the state here would be B prime. So the level, once we put a pulse, the level of intensity starts going down. And look that it takes quite a long time, several milliseconds. Right? So this is a few hundred hertz compared to an LED that you can modulate at megahertz. And this is because we just use voltage to start modulating them from going from this point all the way to this point. But in this work, we look into the fundamental way of operating of LCs, and we notice the following. If you put multiple LCs together, you're going to change the way in which data is mapped from the input to the output. In what way? So here what we did in this plot that you observe here is we changed the voltage. And when we change the voltage, you can see a change in the transparency level. Here, when we put multiple LCs, we also change the voltage. But now you can see that it's colors, like a rainbow pattern. Now, something important to mention here is that we can play some tricks with the polarizers to make sure that the human eye does not see color, just see normal light, but the receiver gets color. Now, what is the importance of this? Look that in this region, the colors are tightly packed. What does that mean in terms of bandwidth and modulation? It means that when we operate the voltage driven on the LC, instead of having a monotonic change like the one that we have here, even up, down, or down, up, we see a non-monotonic change that occurs much faster. So what is the key idea? That instead of choosing the endpoints for modulation, which are these two, like in the first case, A prime and B prime, we can pick closer points, like this A value here and B value here. So for instance, this could be, let's say, A, and this point here could be B. What is the advantage? That now we have reduced by an order of magnitude the time that we require to move from one point to the other. So we have increased the bandwidth, right? The switching speed of this system. What are we paying as a price? We are reducing contrast. So the contrast is not so high. The signal to ratio will be reduced. But as we explained in one of our first slides, that's okay for us because bandwidth improves the capacity linearly and the signal to noise ratio exponentially. So it's a good trade-off to pay. This is our transmitter. The receiver is somewhere at the end of the aisle. This aisle is roughly 60 meters. So we had sunlight coming through this way. There will be a surface here, and then the beam will be sent all the way to the end. This is a zoom-in view of the transmitter, the receiver, which had a lens to focus and try to get more information. And we were able to go from that 80 or 100 bits per second to 1.2 kilobits per second and still maintaining the relatively long range. So we obtained roughly an order of magnitude improvement by looking into these properties of the LCs. How would this system work? Because not everywhere we have light. In the Netherlands, we don't have much sunlight, and many places you may not have either. But in this case, we just look at some data from a Canadian city close to the border in the US. All these gray lines represent 1 day of a year. So we have 365 lines. That gray background represents the radiation from the sun. So for an entire year. And these lines represent the seasons, the average for the different seasons. Now, in terms of power, we have 3 lines. This line, the dotted line at the bottom, represents the amount of energy that we need for this modulation to cover a couple of meters in range. So it can occur very fast because sunlight is very powerful. So you can easily go to a few thousand lux, which is what you obtain with ambient light. But you also need to power the system, and that's when we require a little bit of more energy. Finally, if you would like to have the longer range communication, of course, you will need to wait more and just have that line that you see there. Okay? So that's an idea. So clearly, sunlight, these type of systems will only work during the day and when the weather conditions are not that bad. If you have rain or a very, very cloudy day, of course, this will not be a good option.
So, Marco, sorry to interrupt. We have one question on the similar line. So the question is, can other light sources act as interference for sunlight communication? And if so, are there methods to avoid such interference?
Good question. Short answer, yes. So actually, what we did is when we went for this, after the Accenture, we were invited by Dutch ministries to showcase our platform, this platform here that you see. And we asked to be close to a big window panel where there's a lot of sunlight. We were placed actually more indoors and in front of a big LCD screen that was just showing things, okay? So short answer, yes, you can have interference. And The good news is that because we were using FSK, frequency shift keying, we were able to cope with that interference better. So if you use amplitude modulation, so let's say that you're sending your signals like that, and you use a threshold to distinguish zeros and ones, if there's external noise, now this could change, right? And that threshold will give you erroneous data. But if you have frequency shift keying, it doesn't matter much if there are changes in intensity, because what you care is you apply a Fourier transform to just see the frequency that you are having. Even with that, we had challenges and we need to face a few things. So the short answer is yes, you can have interference, but also you can try to cope with against that, up to a level, of course. If you just want to put a flashlight very close to the receiver, very likely you will saturate it and then things will not work. But that was a good question. Now it's very important to see, so here what we have in this plot is the x-axis is range in logarithmic scale, the same here with the data rate. And if you consider radio technologies, of course, they are somewhere here, right? So we can achieve ranges and very low and very high data rates. And what we are doing now with passive communication is trying to push the Pareto frontier. So maintaining the low power consumption, but try to increase the data rate of our system. Okay, that's the goal. So there has been some initial studies that did some wonderful work at the beginning, and in my team, what we have been trying to do is just to keep on pushing those boundaries in terms of range and data rate.
Okay. Yeah. So sorry to interrupt again. We have one more question, and on the similar lines about the data rate. So the question is, can intensity of light affect the speed of signal communication? And the second question is that what is the biggest design issue in sunlight for wireless communication? So
Okay.
like the first one is more related to the slide that we were discussing.
Yes, so the first question was if intensity could be used or how can it affect the speed? So the short answer is yes, it could be used to increase the speed. So in the same way, for instance, that you have a radio signal, so let me put my radio signal there. And if you have an amount of noise that is like, let's say that, you only can have, let's say, a 0 and a 1. But if I have that same signal with smaller levels of noise, then I can start sending 0, 1, 1, 0, and 1, 1. So if my signal strength is higher and my noise level is the same, then I can start packing more information by having symbols that have more bits per symbol, right? So you can start trying to play the same technique. For example, if we have these transitions that are here, let me just clean this slide. For example, in this case, instead of using transparent and opaque, we can start having intermediate levels as well. So long as the noise is not so strong, and then we can start packing more bits per symbol, okay? Now, so that's to answer the first question. So short answer is yes. The long answer is not as easy as you could do it with light or with radio signals. The second question was, what is the main challenge? We will talk about it in a moment, but the main challenge is just the bandwidth of the system. So optical devices were not designed with having passive communication or ambient communication in mind. They were designed mainly for optical projections for the humans, right? So that means that for radio, we have a high bandwidth. A high bandwidth basically means that we can change a signal very fast. But for these optical devices, because many of them were designed for the human eye in mind, these changes are very slow. So this will require combining more advanced optical technology and at the same time coming up with new modulation or encoding schemes that are not the same as the ones that we used before, but that accommodate to this particular type of platforms. Now, we covered single input and multiple input, and now we are going to go into multiple input, multiple output. So until now, what we have been having is a single surface, so a single pixel, and a single photodiode or photosensor at the end. In this work, it's called Sandbox. What we use is a tiny screen, which you can see it as having multiple pixels. So sunlight will come. This tiny screen will reflect information, and then you can send it back to your phone. And as we mentioned before, you can have information about the city that is there or around. How do we do this? We take a screen that is used for micro projection, but this screen requires LEDs, so it has an RGB LED to transmit information. We remove those LEDs, and we transform the screen to work just with ambient light. So instead of requiring artificial light, it can exploit ambient light. And that's the screen. We had to open it and modify it, and it's very tiny actually. So the basic idea is that we will have sun. This little screen will start modulating a sequence of QR codes, right? So that's how we can transmit data. This will be reflected and sent to the phone, to the camera. Before we were using mainly photodiodes. Here we are using a camera, and then that's decoded by the phone. How does the setup looks like? Inside this box, light will be coming from here. We have the micro display there. Signal is reflected, and you have to place the phone on that. Sorry, something happened here. Let me just. Is everything okay from your side, Sorapa? I had a changing. Everything is okay on your side?
Yes, it is okay.
Okay. And then we get information. The PhD student that did this first experiment communicated a poem. So he was into literature, but I told him we need to do something a little bit more exciting. And what we did is we had preloaded Google Maps, and then we could transmit information, for instance, about the restaurants in our area or the museum. So the phone would be there, and all that data could be transmitted and shown there. We tested this. It can work with any type of light. So it works indoors and outdoors, but because our focus is on sunlight, I'm going to show here the results that we did outdoors. So in this case, we have the x-axis. We perform experiments during an entire day. And the background that you see in yellow is the intensity of light. So it was going up and down, and then there were clouds, and they were clear days. And the different bars that you observe is the different densities of the QR code. So you have a QR code that is big and clear. It doesn't convey that much data. That would be the red bars that you observe. So we could obtain roughly a 2 kbps data rate, but as you can see, it's very constant. Now, we could also pack more information with QR's version 4, and then we could get up to 10 kilobits per second. But as you can see, then it's not as reliable. It can go up and down, depending on the sunlight intensity. And that's a normal trade-off in communication. We also tested different phones. This was done considering also the different densities of QRs. And we could see that the output could change between 2.5 kbps up to 10 kbps, depending on the density of the QR code that you use. So in this way, we can exploit these multiple input, multiple output transmissions. There's also a sort of Pareto frontier that we need to improve here. Oh, by the way, here I'm combining some prior work that we use, of course, as motivation and inspiration. And I'm also putting the work that we did. So everything that has sort of this little flame is tail work that we have been doing in our group. But that's the goal, right? To keep on expanding that Pareto frontier, because it needs to be more competitive if we want it to be a viable solution. And that's the main challenge. And we will see a little bit more soon. Now, until now, I have been talking about liquid crystal displays, but it's important to consider other materials as well. And here I will answer to some extent some of the challenges that were asked a few moments ago by somebody. What is the problem with liquid crystal displays? So with liquid crystal displays, you have these polarizers that are here. And you can see even if I use just one, it already attenuates light, right? It's not so transparent. So what happens is that we have, and before I did this movement, which happens there automatically to change the level of transparency. So what is going on? So light is coming here in an unpolarized manner. We let only one polarization direction pass through. That cuts already 50% of the energy that is going from one side to the other. 50%, and we have not modulated anything. Then this polarization could be maintained in the same direction or change in 90 degrees, and that's how we obtain either a 0 or a 1. So one of the key problems is that we just attenuate 50% of the energy right there. The other issue is, just as I was talking, the switching speed of the system doesn't give us too much bandwidth, right? So here we can see that it's in the milliseconds order, and that's too long. That leads to very low data rates. Hence, one other technology that we look in my group was digital micromirror devices. So this is something that is in your projectors. So usually you have light coming into your projector. You modulate the image in this matrix, and then you project it, and that's what you usually see. What is the advantage of that is that the attenuation is very low. Because they are highly reflective mirrors, you only lose 3% of the energy. And even though these devices are designed to show at 60 hertz, just because that's how we show movies, or maybe at 120 hertz, we develop a new controller to try to modulate them as much faster speeds. And look, the difference here is just microseconds, and here we have milliseconds, right? So 3 orders of magnitude improvement. And the idea is just to try to increase that data rate. So what is what we did? Oh, and here is just actually the improvement on the switching speed that we obtained compared to the liquid crystal displays.
Yeah.
So if we have some light, here's the DMD. Actually, you don't see it, but it's just right here, actually right there. We have the controller. So light is modulated, and then we have a similar receiver to the one that we had before. And we are able to go from those 1 kbps, depending on the distance, to 180 or 40 kbps at different ranges. And then we are still working on this device. One of the challenges is to create a good optical coupling, because you want all the light to be concentrated there and then back scatter, and that's very challenging. But at least the good news is that what we have now is a link with a higher data rate. One of the disadvantages, but that we are improving, is that the link is also very narrow, and we want to make it more broad, so we have a better coverage. Okay, so now wrapping up.
So, yeah, like before we move on to wrapping up, there's one question about multiple input, multiple output. The question is the amount of signal processing that is needed at the receiver, would it not nullify the signal light based power saving?
Excellent question. Yes, to some extent, but so the idea is that, maybe I should mention this. If you have just one single LC, that's microwatt sort of consumption, a few sub-milliwatt, okay? Now, once you start using the DMDs, you start going to several tens of milliwatt, and then the processing is also heavier. Now, there are two important things to consider. These devices have not been optimized just for ambient light communication, but more for video rendition. But the second point is that even if we can go into a few hundred of milliwatts, our goal is just to be competitive with respect to the several watts that we consume with, let's say, a Wi-Fi module or a light module. Of course, we are very far away from it. So the answer to the question is yes, having a more complex transmitter and receiver will start increasing the power consumption that you have. But still, the goal of the research is to try to see if saving ourselves the energy that we use to excite the antenna still will be valuable. And that's sort of where a lot of the challenges are there. And until now, clearly this would not be a competitive technology. So if you have €1 invested on radio communication, it will give you more bits per area, per frequency than on this technology. And then the idea is just have to explore the boundaries of this type of communication.
Okay, so, and one more question, maybe you would answer it in the wrap-up slides. Like the question is, what is the potential for using sunlight for wireless communication in future, and how do you see this technology developing over time?
Those are very two good questions, and that's something that I think I can answer during the wrapping up.
Yeah.
So at the beginning, I show you this slide in which we have the Wi-Fi, light, LED, and then sunlight. So the way that this fits into wireless communication in general is, if you see for the last, let's say, mainly 100 years since Marconi's experiment, our focus has been on radio. And not only radio, but also active. Active means that you need energy to excite that antenna. Over the last 20 years or so, after the invention of the LED, we started looking into visible light communication. So there are many, of course, other optical communication. Infrared, for instance, has been there for a long time. But in terms of visible light of using LEDs, we have been looking for the last couple of decades. And all this is good. So here, by moving from here to here, we are getting a spectrum. But active, so these two quadrants here, consume a lot of power. And there's now a lot of effort in general for sustainability. So 2013, there was this groundbreaking paper that did RF backscattering. So the same as we can use mirrors to communicate with light, but RFID tags that can just use existing radio signals to communicate back and forth with each other, hence just piggybacking on the energy that is already out there. But that still requires man-made signals, meaning that you cannot use the radio spectrum that is coming from space. You need still radio signals that are generated by antennas that we have. And the focus that we are having is just on visible light backscattering. Right? So it's a relatively recent quadrant in the evolution, but what it tries to do is not only get the advantage of a spectrum, but also start consuming less energy. And the idea is to try to develop a network stack that will allow us to insert this into what is traditional network, right? So every time you have technology 802.11, Wi-Fi, Bluetooth, you need a supporting network stack to connect it to the TCP/IP that is already working on the internet. And we are trying to see if we can develop the platforms, theory, and protocols to achieve that. So how would be like the vision or the dream is we could start just seeing our surfaces as means for communication, right? And we have many of those, so not only in our homes or our cities, but we could start seeing transparent surfaces in a lot of different places. Not only that, we have solar panels that now are being used as not only for energy harvesting, but also as a receiver. So then you could have a transmitter that is just working on sunlight, then your solar panel harvesting energy, but when there's communication, maps into a photo sensor. Right, so that could be one of the visions. It's very hard, of course. As you could see, the data rates are very low. The maximum that we are getting now is comparable to what we had 20 years ago when you heard that dial-up connection, 50 kilobits per second. Are we going to be able to make this a viable technology? I don't know, but we are trying. I guess that's the best answer that I can give at this moment. But we're also looking into something else, which is that DMD that I mentioned before, DMD. Imagine a basement where you don't have sunlight. So right now there's something called sunlight collectors that you can place on the roof. They collect sunlight and they use optical fibers. So like you see here, they collect sunlight on the roofs and they use optical fibers to provide sunlight in enclosed environments. And that's good because it's not only illumination, but it gives you vitamin D and light for photosynthesis and all these health benefits. So what we are trying to see is if we can guide sunlight, also use what we are developing and hence have light bulbs, but that they radiate natural light, sunlight, giving you illumination, the health benefits, and communication as well, right? So then we have our ones and zeros here. We are working currently on that by using some of the technology. So overall, if we see sunlight, we could start using some surfaces like windows, but we could also try to carry it to enclosed spaces. So enclosed spaces can benefit as well from this type of communication. Yeah, that's the vision, a city that communicates with sunlight and natural light more and more. Maybe we will have reflective surfaces. Buildings could start talking to each other. I already talked about these sort of panels that could be used in cities. And just to finalize, there's a historical context to this work. Actually, the first experiment of using sunlight for communication was done in the 1880s. By Alexander Graham Bell, the same person, of course, that discovered the phone, and it was called the photophone. So what he did is he was talking with a megaphone. This megaphone will create vibrations on a metallic surface. So sunlight will come, and then his voice will be transmitted, and he had a very basic photosensor and receive it on the other side. So there was analog transmission with sunlight. He got so excited about it that on a letter to his father, he said, I have heard articulate speech produced by sunlight. I have heard a ray of sun laugh and cough and sing. So more than 100 years ago already, the idea of using sunlight for communication was there. It was an analog transmission. Now we are trying to do a digital transmission. But it would be nice to see if we can use a ray of sun now to transmit a video, a text, and images, and then see how far we can go with these new discoveries of optical technology. That's the goal. Will it work? We don't know, but that's the fun part of research, that it's okay if you try and then you can see how far you get. With that, I conclude my talk, and thank you for your attention.
Okay. Thank you, Marco, for this very interesting talk. I'm sure even our viewers found it very interesting. And I hope like this technology takes us more closer to our sustainability goal in communication. And I hope to see this technology being widely used in future. So yes, thank you so much for being here for the talk. And for all our viewers, the next talk is on trust management in social Internet of Things by Barbara Bunova. If you want more information on the upcoming talks or the previous talks, please visit our website, www.connectthemall.net. And yeah, then see you all in the next talk. Thank you. Bye bye.
Thank you. Thank you to you, Sarap and to Ana. Okay. Have a good day. Bye bye.
Bye.